Welcome to my Metallurgy and Material Science class. In this video I will briefly review the major factors that affect the weldability of steels. I said briefly, even though it's more than half an hour, a little bit video. Thank you very much in advance for your patience. I will make your time worthwhile here, okay? I've got some interesting insight here to share on the weldability of steels that will save you a lot of headaches, okay? So, however, this is neither a 4-year degree in metallurgy nor a course of any kind. This is just a single half an hour. To make the most sense out of this half an hour, I'm going to use two things here. One is standard symbols from the periodic table of elements that are the same everywhere worldwide, and I'm going to refer to steel classification or some steel numbering system that I'm going to be using, and it's North American. However, wherever you are in the on Earth, whether you're familiar with the Russian steel numbering system, or the Swedish, or the British, the French, the German, the Japanese, or the Chinese, or Australian, it doesn't matter, because once you're familiar with one, you can fairly easily relate to this North American system. And I'm just going to use a handful of those terms, okay, and it's going to make sense. And I have a table and a half of steel samples set up over there that we can look at and spend 5 minutes on it, just to make sure we're all on the same page, okay? So, as the title suggests, let's get started. As the title suggests, this video is about steels and steels only. So, cast irons will not be considered. Will be mentioned but not considered. Bronzes and brasses and copper alloys will not even be mentioned, or aluminum and magnesium based alloys and metals or any other metals will not be considered. Only and exclusively steels. Second, what do I mean by weldability? Aren't all steels equally weldable? Absolutely not. There are hundreds of steels out there in the world, and there could be, I don't know, 500-800 different types, and just because you welded one out of these hundreds, the other 799's weldability is completely different from the one that you actually welded. What you probably welded, if you welded in high school or you weld at work, is ASTM 836 structural steel, or in SAE terminology it's a 1025 mild steel. Like I said, I'm using North American commercial terminology. SAE is Society of Automotive Engineers, and AISI is American Iron and Steel Institute. They developed this terminology in the 1930s and 40s and standardized it, so that's what I'm using. I will walk you through it in a sec. So in one word, yeah, all steels have different weldability, and in one word, what's meant by weldability is strength. The strength of the weld being produced. Is the weld as strong as the materials being joined together? That's what's meant by weldability. In some cases, the weld is even stronger than the metals being joined together, depending on the skill of the welder and the electrodes and this and that, okay? So, and in some cases, likewise, the strength of the weld that joins the material together is worse than the materials being joined together. Now, that's not necessarily a bad thing. If a weld is for cosmetic purposes only, it's still a valid reason. If there are no great stresses or loads placed on the welded part, a cosmetic weld can work fantastically well, such as holding oil in an oil pan. Oil isn't too hot and it can work fantastically well if it's a cosmetic weld, like I said. So, but what's meant by weldability, how strong is it in comparison to the base metals welded together? Alright, so that's what weldability is. So that also means that in this video I'm not discussing welding technique or welding skills or how to choose the right electrode, how to set up the volts and amps on your welder, or how to apply the shielding gases. That's the technique of welding, and this is the material science or property of material weldability. Alright, so this is only going to be about weldability. So, before we get going with carbon content, let me show you this terminology related setup here. Come on off the tripod and we'll walk over there. Yonder corner in the classroom, we've got this setup here. Carbon steels is the first group here, and in this group there are low carbon steels, mild steels or structural steels, medium carbon steels, and high carbon steels. That's what it says, high carbon steels. In these groups you can see what kind of items are being made of this stuff. In these groups, carbon content evenly and successively increases. So starting at very nearly zero carbon, going up to about 1.2%. Technically, high carbon or anything is defined as steel up to 2.1% carbon content, but past 1.2 commercially nobody makes anything. Okay, between 1.2 and 2.1%. So that's where the high carbon steels pretty much top out. So the difference, other than the difference in material properties of the steels that this increasing carbon content from 0 to 1.2% produces, is quite dramatic. Here the lowest carbon steels here are meant to be bendable and flexible, and you can make these boxes that you bend the metal and crimp it back and it doesn't break, and you can work it with tin snips and hand tools, and these parts are made to be bent without cracking out here where they are being bent, and they work fantastically well for that purpose. These steels here, hollow structural steels, channels, L's, pipes, I-beams, everything, you can't cut it with a tin snip anymore. You need power tools for this one, really. You can try a hacksaw, but good luck with that. So these are stronger as they have more carbon content in them. They are still welded, such as the welded chain link here, obviously welded in the middle, but they are also bendable enough so they can put a strong or a tight radii turn, or sorry, a tight radius turn on this one, and it still doesn't crack out where it's being bent. Now that's the cheap chain. There are also alloy chains, okay, made out of alloy steel, but they start at this carbon content pretty much. And they can make this other kind of chain known as link chain with these pressed plates and pins together. You know, these need power tools to work on, and these steels are stronger, that's why they are structural, than these. You know, this is sheet metal ductwork for the overhead air conditioning, that kind of stuff, and this is for gutters and that kind of stuff. It's also galvanized. Over here, oh yeah, over here as carbon content increases, that's a hacksaw blade, but bandsaw blades are somewhat similar to, or in principle similar enough to hacksaw blades. These blades are welded together. These can be welded, these can be welded. You can see the weld in it there at the bottom. Same for the pipes there. It's an automated welding process. There you can see it's bluing and its discoloration in the heat affected zone somewhat. So that's mild steel there, fantastically weldable. On these things you don't find any evidence of welding anymore, you see. What's made out of medium carbon steels is threaded items, whether it's this one is part of a vise or bolts, threaded or teethed item, with teeth on a sprocket or teeth on a gear, these kind of things. And of course shafts and axles and also wire rope, wire for the wire rope. As carbon content increases, strength of the parts increases. Shafts and wire ropes are a lot stronger than than beams and a lot stronger than the cotter pin. Okay. Or the wire the pop rivet is made with is a lot weaker than the wire rope is made out of, even if the wire is the same diameter. It's a lot stronger wire than the wire used in a wire nail. Okay, high carbon steels. As the carbon content increases, you see strength increases and hardness increases. These items here hold an edge and they should be dimensionally stable, whereas these can stretch and flex and elongate, and beams can sag. If a chisel sags or bends, it's a problem. Whereas beam sag is typically calculated or allowed, or pipes or rebar should sway with a building in an earthquake. If a drill bit, a longer drill bit, twists like so, it's not really a functioning drill bit, you see. These, as carbon content goes up in high carbon steels, they are becoming more rigid. That enables these items to hold an edge. Chisel has an edge, a tap and die set has an edge, the wire cutter part on a pair of pliers has an edge. Okay, hammers don't have an edge, but they are dimensionally stable and they don't deform. Drill bits have an edge and a point, whereas the nail point, or even if you sharpen or make a knife out of this rebar material, it's gonna have an edge, but it's not gonna hold. The nail can be blunted really easily with 1 or 2 strokes of a hardened or high carbon steel hammerhead, you see. So not only they have an edge or a point, such as drill point, but they also hold that edge or drill point, whereas these don't, even if you make one on them. Same way, hand files, razor blades, knife blades, plane blades, screwdriver bits, they hold their shape, they're dimensionally stable. That's what I mean. So this is the pattern that's important throughout these groups. Carbon content up, strength up, edge holding ability up, resistance to wear up. You see shafts and axles, you can easily file a nail, not so easily an axle. And weldability also increases to some degree, and after that not so much. And I'll explain it in a sec. Another group here is alloy steels, and I'm just going to refer to all of these alloy steels, whether it's a molybdenum impact wrench or a chrome vanadium wrench. Everything is just going to be alloy steels without any further distinction. Good quality, other than these tools, good quality gears and gear teeth and good quality crankshafts are made out of alloy steels. The honey and the pencil that's coming with me is part of the explanation. Another internationally used term is stainless steel, and in it I'm going to use, out of the stainless steel groups, I'm only going to use 2, Austenitic and martensitic, because discussion will be about austenite and martensite. Austenite and martensite are crystalline structures of steel, and it's coming up later. From those crystal structures, the groups got their names. The next group here will be featured is high strength low alloy steels, auto body panels and structures of cars and Alaskan pipeline. There's going to be a story on Alaskan pipeline here with high strength low alloy steel. Last group is tool steels. Without any further distinction, everything is just tool steel, whether it's for hand powered and hand driven or rotating electrical power cutter head at a high heat and high speed. Just everything is just tool steel without any further discussion on that one. So these are just a handful of these terms that I'm going to use for describing the first major factor and how it affects weldability. And very simply, as carbon content goes up, weldability goes down quite drastically. Just as the minute amounts of carbon content increases the strength and hardness of the steel really spectacularly, as carbon content goes up, welding or weldability goes down just as fast. So worse with high carbon content, and weldability is better with low carbon content, such as the rebars and that kind of stuff. Okay, the reason for this, in one word, is, let's see, blue, I'm going to spell it here neatly, graphite. That's why I have a pencil here. See, graphite is carbon. These are carbon steels. Graphite is an extremely soft form of carbon. That's what makes it a fantastic material to write with, because it slips, and as it slips and shears, it leaves a nice and even track on the paper. Fantastic for working, fantastic material for strengthening the steels, but it has some benefits as well as disadvantages. It's the softest form of carbon that's out there. And because carbon is allotropic, there are different forms of carbon. The softest is graphite, the next softest is charcoal, and from charcoal we go to coal, and the hardest one is diamond. So unfortunately, out of carbon steels, diamonds don't drop out and spread on the floor and sprinkle. Graphite will precipitate out of high carbon steels. The more carbon the steel has, the more graphite it precipitates out of it as soon as the heat of the welding torch hits it, or welding process. And that precipitation is very similar to this honey stuff. You see, this used to be liquid honey, and over time, as it just standing still at room temperature, the grains of sugar crystallize out of it and becomes this solid blob. Now, the same stuff happens with this graphite content or carbon content in carbon steels. Due to the heat of the welding process, the graphites begins to run together, clump together, form individual little droplets, and those droplets join hands and they form a layer. That layer is like an ice rink or skating rink. That's going to provide a slip surface along which the material will fail. This graphite layer forms in the heat affected zones, and I have a picture of it. It just so happens that, let's see, yeah, that picture. It just so happens, maybe I'll stand over here. This is a book PDF form from the British Stainless Steel Association or some such thing. I'll show you where it's from and at the end of the video. So this here, it says weld. It's a little grainy, but you can make sense of it. This says it's weld here, and it kind of shows, it's a real photograph from a real metallurgy book done on a metallurgical microscope after etching and coloring it and preparing it and everything, okay? And it says 100 micrometers there for scale. So this is for real, and coming from a real metallurgist. I'm not just inventing this stuff, you know. So this is where the weld fusion zone ends. This is the weld deposited, and that's the base material, and this is kind of the fusion zone here, where the weld fused together, and the heat affected zone is further out from the edge of the welded area, and within this heat affected zone you can see these black specks everywhere, and what's written here is graphitization. See, that's what happens with this carbon content, just like with the honey, where the sugar originally is evenly distributed and dispersed everywhere in the liquid honey. Likewise, in the liquid iron, the carbon content is nice and evenly distributed. Then it solidifies as is, and it's fantastically well working as such. But as soon as the welding torch hits it, the carbon begins to run together, and this one just happens at room temperature. And the sugar, as the sugars clump together, first in just one corner and another corner and another one, and then it becomes a solid blob, exactly the same way. One blob of graphite here, another blob there, and they also migrate towards each other, and eventually they're going to form this layer. It's like a butter. You know, that's how graphite works. It just breaks and fails here. Okay, I hope that makes sense. The other two will be faster, because the first factor here affects the second one, and the first and second will transfer to the third one. So we're picking up pace here now. Why people put, and I was just going to mention it, 2 words, why people put carbon into steel is to, again, make steel stronger and make steel harder. This is actually one of the greatest discoveries of the Industrial Revolution, to make steels predictably strong or predictably hard, not just any random alchemist experimenting, the village blacksmith, and it's hoping to kind of somewhat work out. Okay, so measure the amount, precisely measured and controlled amount of nice and pure clean carbon that's uniformly distributed in a matrix of iron and carbon. That makes carbon steel. And that's the village blacksmith, they didn't have enough heat to liquefy steel. All they had was a somewhat red, spongy blob that they had to hammer, and then that's all blacksmith could do. So stronger and harder, and like I mentioned with the drill bits and the chisels, also resistant to wear. Maybe an eraser. Resist wear. Yeah, more resistant to wear. Okay, that's why they add carbon to steels, not to make weldability worse and enjoy precipitating graphite, but to make steel stronger, harder. So the pattern continues to cast irons. Cast irons have 2.5–3.5% carbon in them. By the time you get to white cast irons, the weldability is really in the miserable range. So it starts out as pretty good and even excellent, and then it goes downhill to the negligible. But again, cosmetic welds can work fantastically well. So the next one is alloying element content, and it's exactly the same in its effect as carbon content is. As the alloying content element quantity rises up, the weldability goes down. So with higher alloying element content, the weldability is worse, and with lower is better. There, so same stuff. But the reason for it is different from graphite. In one word, and it's related to carbon content: carbides. Carbides. I'm going to write it here. Carbides are a form of carbon. A form of carbon that's extremely hard and brittle. That makes tools and tool steels actually so hard and brittle that if you have a chisel's edge, you can lose a chunk out of it. With high carbon and high alloying element content, if it's not tempering, and this coming up later, if it's not softened after it's being quenched and hardened, then these super hard carbides will stay in it, and at the slightest shock load, whether it's machining metal or hitting a knot in the wood at high speed, chunks will fly out of it. It's so brittle. So that's how carbides behave. Now these carbides are compounds of carbon and a metal. The metal is the alloying metal in the alloy steels. So if it's a molybdenum steel or a manganese steel or a titanium steel, a vanadium steel, a tungsten steel, a chromium steel, a nickel steel, you get the idea. Whatever metal is the main alloying element, it could be two, or it could be a trimix or a binary alloy, or so if it's molybdenum, it makes molybdenum carbide, tungsten carbide, vanadium carbide, chromium carbide. You get the idea. So These carbides are so hard and so brittle that they make weldability really bad. After being welded, these carbides need to be softened. They do dissolve with heat treatment, namely tempering or normalizing or spheroidizing or process annealing or one of these metallurgical processes. Okay, so that's how carbides can dissolve back into the matrix instead of clumping together and making the tools brittle and pretty much useless for practical purposes. Last one is temper conditions, and temper conditions need a little bit of explanation on these crystal lattices that are over here. There, those ones. Austenite is body-centered cubic, and martensite is, austenite is face-centered cubic, and martensite is body-centered cubic. Over here, I've got this kind of stuff. Austenite here, martensite there. Low carbon, low alloy steels, as they cool and solidify from liquid state, they form ferrites and austenites. When you have high carbon or high alloy content steel, as it solidifies, especially when it's quenched, but even at lower rates of cooling, it produces a lot of martensite and some austenite and very little ferrite. These are very soft forms of steel, or very soft compounds of iron and carbon. So I'm just going to go soft compounds of iron and carbon. Martensite is hard and brittle again. Hard and brittle. Besides the crystal lattice that makes it hard and brittle, what makes it hard and brittle is cementite. Cementite is iron carbide. It's Fe3C. That's how it looks like. All of these are synonyms, so iron carbide, cementite. So when you have a lot of carbon in a steel, it makes a lot of martensite, some cementite, and very little austenite and ferrite. When you have just low carbons, they only make ferrite and austenite. All right. What happens with this martensite and with this cementite that's iron carbide, so that's why it relates to the previous story of carbides, is that you have to anneal it or temper it, or some kind of heat treatment has to be done on it to soften them. But here is the austenite's revenge. Austenite, you see, is body-centered. Austenite is face-centered cubic, and austenite leaks carbon. And as it leaks carbon out, that carbon makes iron carbide compound with the existing iron, and that makes martensite. Even though some of these are being softened and dissolved into ferrite and dissolved carbon, austenite releases a lot more carbon that makes iron carbide than the amount of existing iron carbide is being softened. The reason why austenite contains more carbon is visible here on this illustration here. The atomic number of carbon is 6. Carbon atoms are small. The atomic number of iron is 26. The iron is a big atom with lots of protons, lots of neutrons, and a lot of electrons around it, 26 each. As carbon is a small guy. So the ions sit on the corners of these cubes, crystal lattices, and the carbons can fit in between, you see. And they fit so fantastically well. Whereas martensites have ions sitting on the corner of the cube, even though martensite is technically a body-centered tetragonal, so it's a rectangular prism with it's close enough to cube, okay? So on a martensite, one carbon sits in the middle of this thing, and as an austenite, one carbon sits on every face, so that's 6 carbons. So it contains a lot more carbon as an austenite. So that carbon exits the austenite as it's being heat treated. you're expecting the martensite and the iron carbide to dissolve some of these carbides and soften, but it won't. The revenge of austenite comes right back in and will release more carbon that forms iron carbides than what's being softened by tempering and annealing and spiralizing and any of these processes. They're all the same for now, this discussion. This is real. I didn't just invent it. Here is another reference: delayed cracking of unstable austenitic stainless steel. So this example is from stainless steel, where this cracking happens. This used to be a cup shape. It wasn't cut up into strips like this. This is not a decoration in a flower store. This used to be a solid cup that held liquid. Not anymore. And it splits like this spectacularly because of the delayed transformation of the austenite. And this one says, instead of delayed transformation, it says delayed cracking. Same thing. You can read it, and I'll show you where this PDF is. And it happens during deep drawing. That's a cold metallurgical process done at room temperature, but and it could take months to get this done, or to produce this result. But in welding, it can happen in 15 seconds as the heat of the torch hits the metal. The delayed transformation of the austenite starts, and as it changes crystal structure as well, the shape of it changes as well. It just cracks uncontrollably everywhere. So let me show you where the source documents came from. I'm claiming fair use. I was just pointing at it and reviewing one thing out of it. And it is from the British Stainless Steel Association, there, www.bssa.org.uk, and this is the front page on it. The author is Pierre Jean, and that's how the front page looks like. And on the previous one of this work, I can zoom out a little bit, and its author is up here. Oh, there, that's how it looks like. Electric Power Research Institute, Carbon Steel Handbook. You see, this stuff is real. Metallurgists and scientists research this stuff. And here is this notice that it doesn't need any copyrights, whatever. You can read it. And let me see, there's the author to it. Thank you very much. So going back to this one, we're basically done with this weldability thing. This is how carbon and carbides and graphite and this temper and the existence of austenite affect weldability. To put it together, all of them together, I have them on a graph that looks like this. On the vertical axis, I just invented this. On the vertical axis, I have just subjectively assigned very poor to bad to miserable to somewhat okay, good, better than good, excellent. So that these adjectives are on this side, and I have the steels listed on the horizontal axis. Some steels, you see the carbon content going up, low to mild to medium to high carbon content going up, and there are some other steels. I'm going to explain those in a sec. So low carbon steel, its weldability is better than good. In mild steel, it's even better. There's ASTM 836 structural steel, or AISI or SAE 1025 mild steel. Its weldability is probably the best in all, is the best from among all steels, so all 800 of them, or as many as there are. As soon as carbon content hits, because it has 0.20, it has 0.25% of carbon. As soon as carbon content hits 0.3, 1/3%, it's definitely on the downhill in terms of weldability. And medium carbon steel, by the time you get to 0.5%, it's really downhill. 0.5%, 0.5%. By the time you get to 1%, weldability is really bad. And like I said, it continues. By the time you get to cast irons, 2.5%, 3.5%, it's really in the miserable range. So I hope that makes sense with carbon steels. Why alloy steels are over there is because some alloy steels contain low carbon amounts but low alloy amounts, and as a combined effect I place them next to or in the neighborhood of high carbon steel in terms of weldability. Now some alloy steels are better than others, but as a group, just globally, just all of them are there. Like I said in this video, I'm not analyzing whether how manganese alloy steels work hardened after being welded and how they compare to chrome vanadium steels. That's another story for another video. That's why alloy steels are there. The last on that line is tool and die steels. They are also there next to the alloy steels. Tool and die steels are weldable, but beyond, and sometimes the weld is fairly strong. But instead of fair, they are on the bad side, because now I'm changing the definition of weldability a little bit by adding to it that weldability. I'm also adding into the mix how easily the welder can get a result or get something done. Okay, a cutter head, a titanium steel cutter head. It's made of tool and die steel. You not only have to weld it back together, that's strong enough, but you also have to restore the original geometry of the cutter head, you see. And it's a lot of work. It's not necessarily the welder's work, but I just kind of included it into the concept of weldability a little bit. Because before, once you weld it back together, and it has to be jigged up and properly welded so they are not shifted or otherwise distorted. So once distortion is controlled and it's geometrically as correct as it could be, then before it's sent out for machining, remachining actually, then it has to go through some kind of process anneal. A process anneal takes time and is often done at a third-party provider, service provider, and then it goes to the machinist. That's another guy, and then from the machinist it comes back to heat treatment again, because it needs to be sharpened and honed. That's another process, and once it's done, it needs to be heat treated as well. So after it's being machined, so that it's quenched and tempered to the right surface hardness. Often they need to be case hardened, where the outside of it, it's a differential hardening, where the outside of it and the cutting teeth have a different hardness than the shank of it. So that's why I placed tool and die steels over there. I'm not discriminating against tool and die steels. They are weldable, but it's a miserable affair. It's a long process. This one here is not austenite, it's austenitic stainless steel now. They have a low carbon content and they are fantastically well weldable, you see. Over here we have martensitic stainless steel. Some of them have medium carbon steel, some of them have medium carbon steel amount of carbon, some of them have high carbon, like over 1%, 1.2% for some of the high-end cutlery items and the scalpels and dentistry and surgical items. Nobody welds a scalpel or a chef's knife back together because it doesn't work. Just like welding back a claw of a hammer doesn't work because only for one pull, and then the claw breaks off again due to the high carbon content and graphitization of the originally dissolved and evenly distributed carbon. So it's gonna fit. So nobody welds a chef knife together or a claw hammer back. So that's why martensitic steels are kinda here and kinda here. Some of them are better weldable. Automotive mufflers are super weldable. Alright. High strength low alloy steels are here because they have a low carbon content, they also have a low alloy content, and they are here a little past the fantastically easily weldable, going into the downhill range where they are weldable with caution. But most other alloy steels, besides the low alloy, they are there for this reason. last remarks here for the last 20 seconds is not so much, and the Alaskan pipeline story here is not so much weldability, but a little bit welding technique mixed into it. Steel must be at the ideal temperature for tasks considered. So some of the high strength low alloy steels were developed for cold service environments such as Alaska pipeline, a negative 40 degrees Celsius or negative 40 degrees Fahrenheit, because it doesn't matter which scale it is. That number happens to be the same spot on both of those scales. So if you're welding pipe and the pipe goes through a thermal shock when the heat of the welding process hits it, that's that's going to be cracking everywhere, and that's not good. That's why weldability, the room temperature or service temperature or environmental ambient air temperature affects weldability. But it's more welding technique. It should be taken into a room and should be welded at 50 degrees Fahrenheit or 10 degrees Celsius, you see. And especially if you have thick sections of like anything like 4 inches or thick steel for maybe not for pipelines but for tanks, not tank as in structure, but tank as in military equipment. If you have thick stuff to weld, it's going to be such a heat sink that the heat affected area will expand so rapidly, and the cold area will dissipate that heat so quickly. It's going to crack everywhere. So that thing also affects this temperature consideration. Also is a factor that affects weldability. And it goes without saying, the correct filler metal should be used, so the filler metal should have at least the same strength as the metals being welded together. But again, we're back to cosmetic welding, that also works. Thank you very much for watching. It's been a long video. I hope you learned something and understand a little better how everything works together. Some of the benefits will prove to be disadvantages in some situations when it comes to welding all kinds of steels. But hey, get out there and fix something and weld something and have some fun. Metalworking is fun. Please enjoy life. Thank you very much for watching.